Example 2. The slope of the regression gives the change in Nenana ice breakup date per year. Is there sufficient evidence to claim that ice breakup times are changing? If so, how rapid is the change? So we have the data provided there. We're saying, is there a relationship? So we want to do a hypothesis test for this. We'll start with B1 equals 0, which in words mean there is no association between ice breakup date and year beta 1 does not equal 0, which states that there is an association between ice breakup date and year. So now we need to take a look at the scatter plot before we look at the conditions. I have everything plotted here. We put a line through it. It's not very strong, but there is a linear relationship that is negative. The scatter plot of year and ice breakup date is negative and roughly linear. So now we can look at a residual plot. We have the residuals plotted below. Looks like pretty constant spread, and there's no patterns or trends obvious. The residuals are fairly evenly spread, with no obvious pattern that would prevent further analysis. Okay, now we can look at the normal probability plot. It looks really linear. It lines up very well for us. We don't see really any outliers. A normal probability plot of the residuals is linear with no outliers. The conditions are met. I will use a student's t-model with 89 degrees of freedom. The table only goes to 36, but there's more data available. You'll see that when we open the data and the calculator. So with 89 degrees of freedom for a regression slope t-test. We plug everything in the calculator and we get t equals negative 3.360. Our p-value will be 0.001151. With 89 degrees of freedom. R squared, the variance, is 0.1125, and our R, the correlation, is negative 0.335, so it's not a very strong correlation, but it is there. Our model, we want to go ahead and list that as well, is date hat equals 128.95 minus 0.076064 times the year since 1900. You can see in our table there that that's simply saying year since 1900. It only provides us with years 17 through 36, but our data set has all the values in there. My p-value of 0.001151 is very low, and I will reject the null hypothesis. Even though our R squared is not very strong, there is evidence to suggest that on average, the ice breakup date is occurring earlier each year. So how much earlier? Let's do a confidence interval. So before we can find the confidence interval, I need to find T star with 89 degrees of freedom. In order to do that, I'll use the calculator and do an inverse T. So we go to Statistics, Stat Distributions, Inverse T, and we need to know two things. Degrees of freedom, which is 89, and the area under the curve. Since we're doing a 95% confidence interval, which is two-tailed, but a t-table is one-tailed, we want to do half of that 5% difference, which is 2.5, add that to 95, and we want an area under the curve of 0.975. We hit OK, and it prints out the t-score for us, 1.987. Now we're ready to proceed. T star with 89 degrees of freedom equals 1.987. The standard error of the slope is 0.0226. It was provided in our earlier calculator printout. The margin of error equals T star with 89 degrees of freedom times the standard error of the slope. So our ME equals 1.987 times 0.0226, which comes out to be 0.0449. Our confidence interval is the slope plus or minus the margin of error, so we have negative 0.076064 plus or minus 0.0449. Which gives us an interval of negative 0.121 to negative 0.031. I am very confident that the ice breakup date has been occurring on average between 0.031 and 0.121 days earlier each year since 1900.